Okay, so on this one we're going to be telling increasing, decreasing, or constant from this piecewise function. So again, we know that it continues in both directions forever because there are no points to tell me that it stops. So again, we read the graph from left to right. So as I'm coming up on the graph, is the graph increasing, decreasing, or constant? It's increasing. So at the very beginning, we are increasing, so from negative infinity until, when does it stop increasing? Okay, it's at this point here, 0, 1. And remember, we talk about increasing, decreasing, or constant by the x's. So it stops increasing here at 0. And again, we do not include 0. Then what's the switch? What does it start doing at 0? It is now... It's constant, okay? Because it's flat, right? It's not increasing anymore and it's not decreasing. So we would say that this is constant from 0. And when does it quit being constant? At 2. So from 0 to 2, it is constant. And then what happens at 2? It starts decreasing. And when does it stop decreasing? It doesn't. So from 2 until infinity, it's decreasing. So it's increasing from negative infinity until negative 2. Is that the only place it's increasing? Nowhere else is it increasing. 0 to infinity. Negative 2 to 0, it's decreasing. And constant? Never. And maximum values. Or maybe they just say maximum minimum. Multiple minimums are minima, and multiple maximums is called maxima. Okay, so let's read here. The points at which a function changes its increasing, decreasing, or constant behavior are helpful in determining the relative maximum or relative minimum values of the function. So a function value f of a is a relative minimum of f when there exists an interval that contains a such that blah, 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 blah. Okay? You can tell what minimums are without all this nonsense. So it's like peaks and valleys, right? You have the low points and you have high points. Where the graph reaches low points, that's called a relative minimum, where it swaps from decreasing to increasing. You can see how that's the bottom. It's a relative minimum. Right here is another relative minimum, because the graph is changing from decreasing to increasing. Relative maximum happens in the exact opposite way. So here the graph changes from increasing to decreasing, so you have a maximum value that occurs. And same thing here, from increasing to decreasing, you have a maximum value that occurs there. Here is the important part. The relative maximum would happen at an x value. So you could say it happens at 4. But the maximum value is the y number. So the relative maximum is y, but it occurs at x. Okay? You can see it talked about both ways. So that's another thing people get confused about, because, hey, we're talking about increasing, decreasing, constant. We always talk about x's. Yes. When we're talking about the relative maximum or the relative minimum, it occurs at an x, but the actual value is the y. All right, let's read what they say here. Figure 117 shows several different examples of relative minima and relative maxima. In 2.1, we will study a technique for finding the exact point at which a second-degree polynomial function has a relative minimum or maximum. For the time being, we can use a graphing utility to find reasonable approximations for these points. So eventually we're going to be able to pinpoint exactly where it occurs and exactly what that value is. But for now, we're just going to give approximations using our graphing calculator. Because you just, an example, it tells me to use a graphing utility to approximate the relative minimum of the function. So first thing I would do, I would make sure my zoom is on standard. So I'm clicking zoom and I'm going to go to 6. That's going to put me at a normal XY coordinate plane where I go from 10 to negative 10 in both directions. Then I'm going to click Y equals to type in this equation. So I'm going to clear out all equations that I have, and now I'm going to enter this one. So we've got 3x squared minus 4x minus 2. Then click graph. Okay, what are we looking for? We're looking for a relative minimum. That's good. So a minimum is a low value, right? A low point. So when I graph that in my standard zoom, this is what my graph looked like. If your graph looks something else, you messed up. Okay? So to find out about what that minimum is, I'm going to click trace. And I'm going to scroll down there to where that minimum is happening. So, like, you can see how it goes through your x's and y's. So, like, I see the lowest y value for mine occurs at about 0.606 is where it's occurring at. And the actual minimum value for mine is negative 3.322314. Everybody should be the same if you all click the standard zoom with me. So again, since we're just approximating, we're going to say it's about negative 3.32. It's what the minimum value should be. Okay, now I'm going to show you another way we can find exactly what the minimum value is with this calculator. Okay, so pay attention. Hey, Earth to everybody. There we go. All right, we're looking. We're going to click, it may take me a minute here to remember, second trace. So that's going to be calculate. You should, oh my gosh, are you kidding? That's why I said Earth to everybody. Everybody look at one time. Yes, we got a menu. 1 to 7. Okay, now we're wanting to find a minimum. So guess which one we go to? Minimum, number 3. And click enter. Alright, now it should say left bound question mark. Do you see that?
No.
Did somebody say no? Everybody say yes? That means you're going to go somewhere left of the minimum. So you can pick anywhere on the left side of the minimum and then click enter. Now the next one says right bound. So we're going to go anywhere on the right side of the minimum. And then it says guess question mark. So it wants you to do your best to put where you think the minimum should be. Alright, we had it down there at negative 3.32, right? So I'm going there again, I'm clicking enter. And it will move you to exactly the minimum using that feature. So the minimum happens at 0.666666774. Right? You see that? And the minimum is negative 3.3 repeating. So this calculator will show you exactly where the minimum is. So just by doing our best guess, we got negative 3.32, but the actual minimum is negative 3.33. So again, this is a good approximation. This is an exact answer. So after I have done it, I found that the maximum happens at negative 0.875. And that maximum is 6. So when I look at this, what happens? Well, the graph goes down and it reaches a relative minimum here. Then the graph goes up and it reaches a relative maximum here. Right there, it's real quick. It's happening from one to the other. So it tells me to approximate both the relative minimum and relative maximum. So when I go through here, I'm going to click second, calc, minimum. So now minimum is the low point. So I'm going to go to the left of that minimum, and I'm going to go to the right of that minimum. Then I'm going to guess about where I think it happens. It tells me the minimum occurs at negative 0.577, and the minimum is negative 0.385 if I round to 3 decimal places. Okay, next we're going to find the relative maximum. So I'm going to go to calculate the maximum. So on the left side, I'm going to be as close to it as I can get. I'm going 0, 0. I'm going the origin for my left bound. Then my right bound, I just need to be somewhere on the right of it. I'm going to guess where I think that maximum is occurring. And now once I've done enter, it tells me the maximum is 0.3849, which is 0.385. So this graph has some symmetry to it. Right? The low point is negative 0.385, and the high point is positive 0.385 in those places. Let me say this. Is this the minimum value of the graph in its entirety? No, because it reaches an even lower value here. So this is not the minimum of the graph. It is a relative minimum, which means it's a minimum where the graph changes from decreasing to increasing. That is the low point for that area. And then the relative maximum, again, that's not the highest point the graph ever takes on, but it's the highest point where it switches from increasing to decreasing. Okay, so when I graphed this one, what happened? The relative maximum goes off the graph. Yes. So it looks like this. So what I can do then is I can click zoom, zoom out, and then just click enter again. And then my new graph, I can see all of those key features. Gross. I told you this ain't pretty. It's not pretty. Okay, so I'm going to first find my relative. Which one did y'all find first? Did y'all do maximum or minimum? Okay, good deal. Let's find our relative maximum first. So I'm going to the left of that high point and then just to the right of that high point. You click zoom, zoom out.
It's taken a while, so I'm going to turn my back off because it wouldn't.
You click second on.
It's just lagging.
That was
It's lagging, bro.
We got a bad connection. Okay, so the relative maximum value I found to be 20. The relative minimum I found to be -7. Anybody not able to find those using this calculator? Anybody need help? Okay. During a 24-hour period, the temperature Y in degrees Fahrenheit of a certain city can be approximated by the model, and then they give the equation for that place. Oh, I cut off part of the question. I was excited. They didn't even ask the question. Where X represents the time of day, with x being 0 equal to 6 a.m. Approximate the maximum temperature during this 24-hour period. Okay, so this time I'm having to restrict my domain. The only x's I care about are between 0 and 24. So what I'm going to do, I'm going to go to Zoom. I'm going to go to Zoom Standard, which is number 6. Okay, that gets my graph back to the regular -10 to 10 in both directions. Now I'm going to click Window. I want to restrict my x's to only those between 0 and 24. So I'm going to go to X-min is 0, X max is 20, I'm going to go 25, well, I'm going to go 24. I don't know what I'm going to do. I'll go 24, okay? So all I can see are the elements between 0 and 24. Everybody here on window? Everybody follow what I'm saying? Now what's the Y values measuring? They are measuring the temperature. Well, does it make sense for my Y's to only be between -10 and 10? Not really, so let's think about what temperature could be. Let's put -10, let's leave that what it is, because we don't know, this could be during winter. Right, so let's just leave it at -10 and see what happens. But the maximum, sounds good. Let's go 120 degrees. We could be in Arizona. Right? I mean, we don't know anything about this city. But now the Y scale, that's how much each tick mark counts. Since we have a wider range, I'm going to make each tick mark be worth 20. So I'm going to make the Y scale 20 instead of 1. Right? You could make it 10, 15. You just need to know that it needs to be a little different. Okay, now I'm going to click Y equals, and I'm going to enter in this equation. I wonder if I put it all in correctly. I did not. I knew something did not look right with that graph. My graph, the temperature went up and just kept going up. I mean, it was scorching by the end of the day. That looks better. Yeah, there we go. It's like a wave. So right here is what my graph looks like. And again, yours should look the same because we have the exact same values for the scale. Right, now if you picked a different window, your graph could look a little different. If you picked the same window as mine, that's what it looked like. So I'm looking for what? I'm looking for the maximum temperature of that day. Well, I can see that that maximum occurs right here, is the relative maximum. So I'm going to go and use my calculator. Click calculate the maximum. I'm going to go to the left of that wave. Then I'm going to go to the right of the wave. And it tells me to guess. So when I have done all that, it then tells me the maximum. So the relative max is 63.928 degrees in Fahrenheit. So yes, after you run your relative minimum, don't worry, I'm re-recording over it so nobody knows we messed up. The relative minimum here is 33.9809. 54. So it should be 33.981. Okay, so this is called the greatest integer function. It's denoted by two brackets with an x inside of it. And it's defined as the greatest integer less than or equal to x. It has an infinite number of breaks or steps, one at each integer value in its domain. The basic characteristics of the greatest integer function is summarized below. So the domain, it includes all x values. So like, we can't see it, but it's continuing forever. But look how it goes. It goes from -3 to -2, -2 to -1, -1 to 0. So for every hole, it picks up right where that one stops. So the domain is all real numbers. Okay, what about the range? What are the y values? Okay, well, down here it goes all the way to negative infinity, right? But it doesn't happen at every y. It only happens at integers. Every whole number or negative whole number, right? That's an integer. All the y's between never happen. So we would say that the range is the set of integers. It's all those whole numbers and their opposites. Right? That's what an integer is. X-intercepts. That's where does it cross the x-axis? Well, it crosses the x-axis here, and here, here, right? All of these are x-intercepts. So we say the x-intercepts is every value between 0 and 1. Notice, we include 0 because it happens here. But at 1, the graph jumps. So it's no longer here at 1. So those are my x-intercepts. The y-intercept is the origin. That's the only place it crosses the y-axis. Because right here it gets right up to the y-axis but never hits there. It only crosses at 0. It's constant between each pair of consecutive integers, and it jumps vertically 1 unit at each integer value. So this is called the greatest integer function. It's also sometimes called a step function. Can you imagine why?
No.
Looks like step. Yeah, exactly. Okay. So I will sometimes call it. I normally call it a step function. Okay. So this is something that there's a couple different ways you can do this. All right. We're going to now sketch a piecewise function. So what's a piecewise function? It's where we've got these two parts of my function that are defined for different x values. One way you can do it, you could graph all of this line, you could graph all of this line, but then you have to erase the parts that need to be erased. Like, for instance, I'm just going to use their answer over there. So you see how they've already erased parts of these lines. But if you were to graph both of these lines, you'd have a line here that has an x-intercept at 4 and a slope of -1. And then you would have another line that would be here. That's the line with a y-intercept at 3 and a slope of 2. Right? Those would be my two lines. Now, you have to graph them in their entirety, and then you have to erase parts of it to make it work. So, because I'm looking here for where x is less than or equal to 1, then I'm only looking, I'm going to go to 1 for that line, which is here, and I'm only going to include the things that are left of it. So I have to erase everything from there, right? And then I'll need to do a colored in dot because that part is included because it's less than or equal to 1. Alright, then you'd have to go over here. We're looking at this line. It is only good when x is greater than 1. So it's good from here to the right, but it's bad to the left. So I need to erase all of this. And because at 1 we are not including it, then at 1 we need an open circle. Right? And you can see that process, kind of how I've done that. When I graph piecewise functions, I don't like graphing the whole thing because then I have to go erase. I'm not a good grapher in the first place. I'm an even worse eraser, right? It's no good. So, I'm going to show you the way I would work this problem. What I just did, you can do it that way. But you won't ever see me do it that way again because I don't like it. But it's valid. And that works better if you only know how to graph using slope-intercept form. Y equals mx plus b. Okay? But that's not the only way to graph. So here is my thought process if I were to work this problem. Let me get my graph. Okay? Here's how I would work it. I would see at 1, I have some interesting things happen. So at 1 here, the graph should be good and included. But at 1 here, the graph is not included, and I have a hole in my graph here at 1. So let's work these one at a time. I'm going to start with the top piece. So I know when x is 1, I got some things going on here. So if I plug in 1 for x, what is my y value? 5. So I know 1, 5 is a point that's included in this top piece of my function. So I'm going to go to 1, 5, and I'm going to fill in that piece. And I know that's the end of it, because I'm only using x's that are less than or equal to 1. So this line's going to go all the way up to here and stop at that point. So I found exactly where that point happens. Yeah. Boom. Okay? Now, to make a line, I need what? I need 2 points. So if the slope of this line is 2, that means I could rise 2, run 1. Okay, but that puts me over here where I don't want to be. So I can go the other direction. I could go down 2 and left 1. So if I go down 2, left 1, I find another point on that line. And again, you could do this as many times as you wanted to. Down 2, left 1, down 2, left 1. Okay, and so right here, I've messed up somewhere. Hold on. Woo, yep, that was bad. I knew that line looked like it was curving. Down 2, left 1 should be here. My fault. That looks better. Well, still not a very good line drawer, but it's definitely better than it was. Okay? So that's the first piece. I've graphed it. Now the second piece is going to be here. Now it doesn't start until I'm at 1. So I'm going to plug in 1 there. So that if I plug in 1, I'll get -1 plus 4, which is 3. So that means the point 1, 3 is on that line, but that is not included because it has to be greater than that point. So I'm going to go to 1, 3, and I'm going to put an open circle at 1, 3. And now I know the graph is going to the right from here, so the slope is -1. That means I could go down 1, right 1. Down 1, right 1. Down 1, right 1. And I would connect. Well, I would try to connect the dots. And so that's the way I would graph it. So I'm not using Y-intercepts. I'm using that main point where the graph swaps from one to the other. And then I know which direction they're going, and I'm just using the slope to find the next points on that. Yes?
Could you use the arrows to figure out which way to go, or greater than or less than? That's what, pointing that way, or is that not?
You have to know how to read it, because you can have some that are 3 pieces. And so if you have a third piece, you're going to have one part that says x is less than or equal to -2. Like when you have 3 pieces, one piece is going to look like this, and it's sandwiched between them. So you can't just say, all right, it's pointing this way, so it goes that direction. You got to know x is between -2 and 2. We'll look at one like this right tomorrow, but we'll plug in both endpoints for that piece. Both lines and then erase the parts that are not included. That's not the way I do it. I plug in the values that are given here as critical points. So first, let's plug in -4 to this equation. So if I plug in -4, -4 times -1/2 is 2. 2 minus 6 is -4. So in the top one, when I plug in -4, I get out -4. So I'm going to go ahead and graph that piece of my function. So I go to -4, -4. I've got a point there, and that point is included. So I'm going to fill it in. I know it's included because it says less than or equal to. Now, if the line has to be less than -4, then that's going to be everything to the left of -4. So I need the line to go in this direction. So I'm going to use the slope going left. So that slope tells me I could go down 1, right 2, or I could go up 1, left 2, if I put the negative in the denominator. So I have to do that. So I'm going up 1, left 2. Here's the next point on that line. And then I'm going in that direction forever. So that's the bottom piece of the function. Now to find the second piece of my function, I'm going to plug in -4 for x here. If I plug in -4 plus 5, I get out a value of 1. So now on my graph, I'm going to go to -4, 1, which is right here. Now this point is not included. It has to be greater than this. So at -4, 1, I'm putting an open circle. And then I'm going to use the slope to find the next few points. So the slope here is +1. So I could go up 1, over 1. I could do this as many times as I would like. And again, that line's only going towards the right because it has to be things greater than -4, which would be to the right of -4. Okay, so here we're going to look at these graphs and we want to determine, are they even, odd, or neither? So when I look at this one, does this have symmetry with respect to the y-axis? So symmetry with the y-axis, that is an even function. B part, does that have symmetry? It does with respect to the origin. So this one is an odd function. C part, does that have symmetry? It has symmetry, but it has symmetry with a line here, right? Is that the y-axis? Is that the origin? No, so it's neither. It's neither even nor odd. And D part, does that have symmetry with respect to the y-axis? Yes, even. This one would be even. It has symmetry with respect to the y-axis. Okay, so this is how we tell if it's even or odd without graphing. All right, this looks real confusing. What's happening? They're plugging in -x, and they're getting the same thing as if they plugged in +x. So if I can plug in -x and I get the same thing back, it's even. So let's write that down. If I plug in -x and get same thing back, it's even. Now the second one is for when it's odd. Okay, if I plug in -x and get opposite signs for everything, then that is an odd function. So just like graphing piecewise functions, my students struggle with this every year. So I'm trying to break it down as simple as possible. I'm going to work 3 problems, then we're going to let you work 3 problems. Okay, so we want to determine whether each of these functions is even, odd, or neither. And we're going to do it without graphing. All right, so I'm starting with A. So what did I start with? I start with g of x equals x to the third minus x. Now I'm going to plug in a -x. That's how we determine both even or odd. I plug in a -x. All right, so what does that mean if I'm plugging in -x? Everywhere there used to be an x, now I'm plugging in negative x. Just like what we've done before. So this is now negative x cubed minus negative x. Everywhere there used to be an x, I'm plugging in negative x. Now we simplify it to see what it's going to look like. If it looks exactly like this, it's even. If both signs are different, it's odd. If neither one of those things happens, it's neither. Okay? So let's watch what happens here. What is negative x times negative x times negative x? That's negative x cubed. When I multiply negative 3 times, it's a negative. Now, what is minus negative x? Plus x. So I plugged in negative x, and what happened? I changed the sign of both terms. Therefore, this is an odd function. Okay, B part. I've got h of x equals x squared plus 1. To determine if this is even or odd, I'm going to substitute in a negative x. So I now have h of negative x. So that's going to equal negative x squared plus 1. Now what is negative x times negative x? It's going to be positive x squared. Nothing happened to the plus 1, so it comes down. So now my function is what I started with. I plugged in negative x, but I got back what I started with. This is even. Okay, then the last one. I've got f of x equals x cubed minus 1. To determine if this is even or odd, I'm going to plug in negative x. So now I have f of negative x. That's going to equal negative x cubed minus 1. Negative x times negative x times negative x is negative x cubed. Nothing happened to the negative 1. Did I get back what I started with? No. Did I change the sign of everything? No. This is neither. Okay, A part. We get even, odd, neither. It is neither. B part. Even, odd, neither. Even. C part. Even, odd, neither. All right, are y'all sensing a pattern on this? What's the pattern?
If there are only X numbers, then it's automatically going to be odd. Even,
Not necessarily.
Even exponents, it's going to be even, and when there's odd exponents, it's just going to be the odd.
If all of my exponents are even, it's an even function. But they all have to be even. If I have a mixed set where some are even, some are odd, it's going to be neither. Right? If all of my exponents are odd, then it's going to be an odd function. All right? Some of you may be asking, well, what about this? This doesn't have an even exponent. Actually, it does. Okay? If I have a constant term, that is really x to what power? X to the 0 power. Right? Negative 1 is just negative 1 times x to the 0, which is an even number. Right? The 0 power makes it an even power. So constants are the same as an even power. That could be the one little trick in there. Main
is all values between -4 and +4, and those are included. Now the range would be the list of y values. So again, I'm looking for the lowest one first. So there's nothing. Right here is the lowest y value the graph takes on. It's at 0. That's included. And then the highest y value the graph takes on is +4. And it takes on everything between there. There's no gaps or holes or spaces. So the range will be from 0 to 4. Okay, then they ask me these 4 questions, right? So what's the function evaluated at -4? So when my x value is -4, what's the y value? 0. Next, what's the y value when x is 0? So I go to where x is 0, the y value is 4. You follow? Now function evaluated at 2. So I go to where x is 2, what's my y value? They went with 3. It's close enough. Right? I don't know if that's exact. We're not looking for exactness. And then right here, the function evaluated at 4. So when I go to 4, the y value is 0.